First of all, thank you everybody for being here, and also the organizer that invited me to give this talk, which is going to basically summarize the result of our recent hackathon. I believe it was the end of July, and was focusing on OpenACC optimization of one of the main BerkeleyGW module, which is actually named as the Epsilon module. So I'm going to start with a brief introduction and motivation why we're doing this work. Then I'm going to give you a little bit more details about the Epsilon module of the BerkeleyGW software package, which we have been working on. I'm going to then present the baseline performance of the starting port. And then I'm going to give you some details about the various steps we have taken in order to achieve better performance or improved performance by using OpenACC. And finally, I'm going to summarize with the main achievement. So to start with a brief motivation, you probably know that material science and chemistry codes such as BerkeleyGW are among the most heavily used on HPC facility all around the world. And the trend is going to continue in this direction. And the reason is that this kind of application gives you important information that are necessary in order to understand the fundamental electronic and optical properties of materials, which are necessary in order to design novel components for new generation devices. And the applications are wide. I mean, they range from quantum computers, batteries, photovoltaics, catalysis, and so on and so forth. So for over 3 decades, density functional theory has been the workhorse for this kind of application. And the reason is that density functional theory provides you for an excellent compromise between the accuracy and the computational efficiency. On the other hand, density functional theory is a ground state theory, so often give problem when trying to reproduce excited states phenomena. And actually, excited states phenomena are really the focus for next generation technology. Here is an example, is a defect, point defect in a semiconductor, in particular in silicon, but as well silicon carbide. And this kind of system are very interesting because it serves, for example, as prototype for solid state qubits. So what is important here is that you're not really interested into the ground state, but you're interested once the electrons are excited from the ground state to some excited level, shown here as the red line, right? So there are 2 main challenges associated with the simulation, first principle simulation of this kind of system. The first one is the level of accuracy. Since you are interested in excited states properties, you need to go beyond density functional theory. So I'm going to present about advanced method based on GW and the GW plus Bethe-Salpeter Equation. And increased accuracy as usually means that also the computational cost of your application grows. And the second challenge is that usually you are dealing with system with a broken symmetry. In this case, for example, is a defect. So in order to decouple the periodic images, when we are working in periodic boundary condition, you need to have a reliable simulation. You need to use a much larger simulation cell for per crystal. That means order of thousands of atoms or tens of thousands of electrons. And these already pile up on the increased computational cost that you have from the increased accuracy. The good news is that this is actually a great application to take advantage of massively powered GPU accelerated system, thanks to the fact that, in fact, you are increasing massively the amount of flop you need to achieve completion for your calculation. Now, BerkeleyGW, I've been mentioning, is implementing the GW and the GW plus Bethe-Salpeter Equation. Is a general purpose software package, which is used exactly to study the excited state properties of electrons in materials. Here are some of the highlights, recent highlights, showcasing the kind of science you can do with BerkeleyGW. You can simulate at the highest level of accuracy with application that, again, has a wide variety of possible implication, for example, in quantum computing, energy storage and conversion, photovoltaics, nanoelectronics, and so on and so forth. Now, how do we position ourselves in the direction of Exascale? So we know for sure that at least within the DOE Office of Science, the path to Exascale is going to be GPU accelerated. And here is shown briefly the kind of timeline that we're expecting here. Now, we started here back probably 10 years ago, optimizing our application. Back then, the model of the programming model for the many-core architecture was clearly OpenMP on the CPU. And after optimizing our application, we have been able to scale to the entire system. A NERSC at that time was Cori, the KNL partition. We scale to more than 500,000 cores, and we achieved more than 50% of peak performance, which at that time was 11 petaflop. Then the GPU revolution came about, and so we had to start working to port our application to take advantage of that kind of hardware solution. And back then, there were not that many options. CUDA seems to be the most promising. And after a few years of optimization, we have been able actually to scale to the entire Summit system that a couple of years ago was the #1 supercomputer in the world. So here, meaning 27 more thousand GPUs, also achieving more than 50% of peak performance, so a little bit more than 100 petaflops second. So how do we position now going forward? Well, we know that the future system are probably not going to be NVIDIA, so especially in the timeline, we're going to have Intel GPUs, AMD GPUs, and essentially the promised programming model to achieve true performance portability, it seems to be OpenMP Target. On the other hand, OpenMP Target is not yet fully mature as a programming model. So our strategy is to move one step forward by doing a portability strategy, starting with OpenACC, which is much more syntactically similar to OpenMP, with the hope that we are going to be able to translate easily from OpenACC to OpenMP Target. And as I'm going to show, and actually some of the experience we had at various hackathons, these approaches actually seems to work very well. Now, again, BerkeleyGW, there are 4 major modules, Epsilon, Sigma, Kernel, and Absorption, which implement the overall workflow of the GW plus Bethe-Salpeter. But today, I'm going to focus only on the Epsilon module, which is the starting point, which has been also the focus of the hackathon a couple of months ago. So let me start talking, giving you a little bit more details about Epsilon. And in Epsilon, we can recognize 2 major computational kernels. One is called MTXEL kernel, is based on FFT transformation, fast Fourier transformation, is the 2 nested loop. The outer one is usually of the order of 100 iteration, the innermost is usually of the order of 1,000, and it's doing kind of a simple set of operations. So it's a put, which goes from a vector to a sphere into the box, an FFT, a pairwise multiplication of the 2 boxes, another FFT, and then another step to get back from the sphere to the vector. So we had an OpenACC initial implementation, which is essentially using a single stream for all the kernels, and also is not employing any kind of blocking of the innermost loop. The other most important kernel is Chi0, which is by far the most computationally intense kernel for large-scale application. Is essentially implementing a large distributed matrix multiplication between short and fat matrices. And to give you an idea, for a very large application, the number of rows can easily be of the order of hundreds of thousands, and the number of columns can easily exceed hundreds of millions of columns. So truly a large-scale kind of application. And our initial port on OpenACC was very simple. We simply offload the data from the host to the device before performing the ZGEM, so using the CUDA library in particular. So let me show you the baseline performance. We have measured before starting the OpenACC optimization of the Epsilon module. And most of the results I'm going to show you are going to be obtained on the Cori-GPU cluster at NERSC. Each node has 8 V100 GPUs and 2 sockets of 20 cores of Skylake Intel CPU. We're using a relatively small benchmark system, and we are also comparing the CPU-only run, where we use 20 MPI tasks and only 2 OpenMP threads per MPI task, with the GPU run, which use 8 MPI tasks and 1 GPU for each of the MPI tasks. Now, here we start first comparing the CPU-only implementation with the initial OpenACC port. And you see that we already have a relatively nice speed up compared to the CPU version. So this very simple first implementation already achieved more than 5x speed up. And in particular, both of the kernel have been speed up of more than 5x. Now, also interesting is that we have the 2-port OpenACC and OpenMP Target, which can actually compile simultaneously. We can switch between the 2 implementation. And it's very nice to see that we achieve a very similar performance for the 2 kernel, I would say almost identical. But most importantly is that now if we compare to the OpenACC model with the CUDA, which we consider as the ceiling of performance that we can achieve on NVIDIA hardware, we still have room for improvement. So overall, we can in principle improved by 2.4x, and each of the individual kernel can also be improved dramatically by optimizing the ARP. Now, we also collected some data on the DGX node on Cori, which are more similar in terms of hardware as the next generation, which is the newest supercomputer at NERSC, which is Perlmutter. The main difference is essentially the CPU is Skylake versus AMD Rome. And instead of having 8 V100 per node, on DGX, we have 8 A100 per node. So already the CPU does a decent job improving the performance. And also when we compare the OpenACC implementation, just essentially changing the hardware, we get for free 1.5x without doing any optimization. A little bit different the situation than before. So OpenMP Target, it doesn't really achieve the same performance as well as OpenACC. And also the CUDA gives a moderate speed up, just switching between the two hardware. Now, let me just summarize now the kind of optimization we did for the MTXEL kernel. Again, MTXEL kernel is implementing these two nested loop. The outer loop goes over this we call valence vector, and perform just a put and an FFT operation. And then the innermost loop, which run for large scale application over 1,000 of cycle, perform again a put operation going from the vector to the sphere in the rank 3 tensor, perform the FFT, then we pairwise multiply the two boxes, another FFT, and then we get back from the sphere to the vector. And again, the initial implementation, just a single stream, and we don't block the innermost loop. So we just perform the entire cycles of the innermost loop without actually blocking the loop itself. So we started with the baseline profile of this original kernel. And what immediately we see is that it's pretty simple to isolate each of the individual kernel for the innermost loop. And we noted that we have these data transfer that are kind of breaking between the various computational kernels. And we realized that these are actually associated with the memory transfer of a small array, the NFFT, which is only 3 integer elements which actually specify just the size of the 3D FFT. So since each of the FFT is basically identical, we can just offload this small array at the very beginning and just don't copy it for each kernel execution. And this already gives a very nice improvement. And you can see now that all these kernels are executed one after the other without having to copy back and forth this small array. Now we look at this first kernel is this essentially copying the data from a vector to a sphere inside the box, the 3D box, before running the FFT. And somehow this kernel is taking a large fraction of time. We don't expect that to happen. Actually 30% for this innermost cycle of the MTXEL kernel. So what we can do, we can play around with the kernel. What we did was essentially just switch from OpenACC parallel loop construct to the parallel loop gang vector and specifying a vector length of 512. And just doing that for the put specific kernel, we essentially speed up this operation by 3x. Now the fraction of time spent in this specific kernel is only 8.5%. What is interesting here is that multiply and get have a very similar structure as the put, but just switching from the parallel loop construct to the vector length and loop gang vector, it doesn't really give a huge improvement. It's just a few fractions of a second. Now, the second strategy here to improve even further performance was to introduce streams. So we can actually break the innermost loop into blocks. And for each of these cycles, we can assign a stream and then schedule the data copy on this stream, as well as all the put, FFT, multiply, and get on the same stream for each different cycle. So it's interesting here that actually the kernel execution achieve relatively good overlap between the different kernel, but the mem copy is not actually overlapping with the data execution. And we realized that this is probably due to the fact that the data transfer is too large. So somehow the compiler forced for the blocking of this data operation before the kernel execution. So what we can actually do is instead offload of the the innermost kind of vector before actually entering the innermost part of the two-nested loop. This might be potentially a memory bottleneck, but thanks to the fact that we introduce a blocking of the innermost loop, we can easily control the size of the array we are transferring at the very beginning. So as you can see now, the innermost iteration is executed one after the other. We don't have memory transfer in between the two, and also we achieve a very good overlap between the various kernel execution. And so we went down essentially from 64 seconds at the beginning with our simple implementation down to 18.5. So overall a 3.5x speed up, which looks very promising. So here I'm summarizing all the steps we have taken in order to achieve this kind of performance. Something I want to note is that we also experiment by using the batch FFT, and very interesting and promising is that the batch FFT, which is much simpler than using streams, to be honest, is actually achieving very similar performance and might be the good strategy looking forward for performance portability across various architectures. I'm probably going to skip this one. Let me briefly also show you the result for the chi-0 optimization. Again, these large distributed matrix multiplication, short and fat matrices. The original implementation, very simple, offloading the matrix elements before executing the ZGEM. So similarly to the MTXEL kernel and with the lesson learned with the CUDA implementation, we have implemented two main strategies here to improve the performance. The first one is to introduce the stream and also offloading all the matrix elements to the device. So we don't have this continued mem copy from host to the device, but a simple large mem copy at the very beginning and just extracting the data after the ZGEM. The advantage of this kind of implementation is that using stream, you can effectively overlap the MPI communication on the host with the ZGEM execution on the device. So of course, to do the offload, we had to write some kernel. Here is just a summary of the kind of kernel we had to write, for which we can also assign, of course, the async, so the stream. So everything is nice and running one after the other without actually losing data when we do the mem copy. So here to summarize the profiling at the very beginning, as you can see, is clear the data copy before the ZGEM execution. And now with the improved code, you can see that the ZGEM just run one after the other. We have just a little bit of mem copy, and the MPI communication actually overlap with the execution of the ZGEM on the device. So let me summarize the result here. At the beginning of the hackathon, we were not that competitive with the CUDA implementation, but at the end of the hackathon, we have been able to achieve an overall 2.5x speed up compared to the baseline model. And both of the kernel, MTXEL and chi-0, have been accelerated for more than 3x. Now, most importantly, if you compare the CUDA implementation with the OpenACC implementation, we achieve very similar performance. And this might not be the case for a larger application, but is, of course, an encouraging result at this stage. So the thing might be a little bit different once we move from 8 GPUs to 1,000 or tens of thousands of GPUs. So this is still some work in progress we're working on. So to summarize, we have optimized for OpenACC programming model the two major kernel of the Epsilon module of BerkeleyGW. The MTXEL took advantages either of streams and blocked implementation or the batch FFTs, which achieve very similar performance. And chi-0 take mainly advantage of reduced memory copy as well as overlapping the MPI communication on the host with the ZGEM on the GPU. And overall, we achieve more than 2x speed up, and each of the individual kernel more than 3x. And most importantly, the OpenACC implementation at this stage achieved very similar performance as the CUDA implementation that we consider to be the ceiling of performance for NVIDIA hardware. So the next step is actually implement some blocking mechanism for chi-0. Offloading all matrix elements might be a memory bottleneck for large-scale application. And also in the long term is to achieve similar performance by using the OpenMP Target programming model. And with that, I've finished my talk, so I thank you again for your attention.